So today we have several topics. We are going to start off doing trig proofs, verifying trig identities, and we're going to go through a very specific process. It's not going to be a two-column proof, but just like two-column proofs, you can't do any steps in your head. You have to write every detail down as we go through these. So before we jump into those proofs, I want us to review some of the things that we will be able to use in our proofs. One of the things that we know is a whole list of reciprocal trig identities. So if we're doing a proof and we have the secant of theta, it is okay to change that to 1 over the cosine of theta. If we have the cosine of theta in the proof, we can change that to 1 over the secant of theta, and so on for our other reciprocal identities. When it comes to tangent and cotangent, we can say tangent is 1 over the cotangent, cotangent is 1 over the tangent, but we also have another thing we have learned for tangent and for cotangent. We can also change them to sines and cosines. This is a review. You already have these in your list from lessons 29 and 41. Tangent is sine over cosine, and cotangent is cosine over sine. Now, when we are doing trig proofs, here are the steps that we are trying to follow. We are proving things that are true for all angles. It's not that, oh, this identity is true if the angle is 90 degrees. Or this one's true if the angle is 45 degrees. It's true no matter what the angle is. We're going to prove it in general. To show that an identity is true, we are going to look at what they say, prove this equals this. And we are going to pick one side and write that down without any changes, exactly like it shows up in the book, but just one side of it. And usually it's going to be easier if we start with the messier side and try to simplify it to something that looks cleaner. Then we are going to do that first side equals something, 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 equals the second side. So it's going to be one long equation. First ones are going to be really short. They're going to usually be something equals the second side. But we're going to get to ones throughout the semester that get longer and longer. The idea is to get one long equal string. One side equals other things equals the second side. You do not do these like solving an equation. You may not write down both sides and do the same thing to the left and to the right as you work your way down. That is not verifying a trig identity. So the things that we may do as we go through these steps, we write down one side. If we have one of those reciprocal identities we just talked about, if we have secant theta in there, we can substitute in 1 over the cosine of theta for that, or anything else that's equivalent. Another thing that we can do is we can multiply by 1. If we have a term, we can multiply it by 1. Now, if we just multiply by 1, that doesn't really do anything. But if we multiply by sine of x over sine of x, that might help us have some things that cancel out and simplify. The other thing that we can do is we can combine like terms. If we have the cosine of x plus the cosine of x, we can say 2 times the cosine of x. Or if we have two things with the same denominator, something over the sine of x plus something over the sine of x, we can combine those as one fraction by adding the numerators. Those are the 3 things that you may do when you are verifying trig identities. And as I said, start with one side and change that and change it again and again, show every single step, but you don't move things from one side to the other. That much sort of makes sense so far. So let's start out with a couple of very simple trig identities. So the book will say things like show cotangent x over cosecant x equals cosine of x. First thing we need to do is to decide which side we want to start with. So you decide left or right which looks messier, and I'm going to take your vote. How many think left looks messier? Okay, that's pretty much every hand going up. So we will start out with the left-hand side. You write it down just like it is. No mental math. I know that's a challenge for some of you. You always want to do as much mental math as possible and as little writing, and that's not okay when it comes to doing these proofs. So we've written that down. And then we're going to think about the things that we know so far. And so far, we just have those reciprocal identities and the definitions of tangent and cotangent in terms of sine and cosine. So far, that's all we have that we can use. We'll get some more in a few minutes. So cotangent. If I write that as its reciprocal, 1 over what? 1 over tangent. I wonder, do you think 1 over tangent is really going to help me get closer to cosine? Not really. So what else can I do with cotangent? What's my other choice for cotangent? Cosine over sine. So I'm going to rewrite this cotangent of x as cosine x over sine of x. And I purposely just modeled it for you that way. That's going to be the process with a lot of these proofs. You're going to say, well, what's one thing I can do? Will that really help me? Probably not. What's something else I can do? You'll do that a lot through the rest of this semester as you're proving identities. It does not have to be the right idea is always the first thing that jumps in your head. It's okay to think about one and say, I'm not so sure, is there something else I could do instead? What can I do with cosecant? What can I do with that one, Reed? So 1 over the sine of x. Everybody good with that so far? Now we've got a complex fraction inside of a fraction. And what do we do whenever we have fractions inside of fractions? Mia? So what we typically do is we multiply by the least common denominator of all of the little denominators. So if I multiply by the sine of x over the sine of x, I'm multiplying by the least common denominator of these little denominators. Is that something I'm allowed to do with those 3 rules? Yeah, I'm just multiplying by 1. And when I do that, sine cancels in the numerator, sine cancels in the denominator. I'm left with cosine x over 1. I don't leave the over 1 because I can simplify more. Cosine x divided by 1 is just cosine of x. Is that my right-hand side? So I have one long equation. First side equals second side, and I'm done. Questions on that one? You've just done your first trig proof. Let's do another one. Kind of a toss-up on this one, which one's messier. Right-hand side has a fraction in it, and the left-hand side doesn't, but the left-hand side has 2 different trig functions. So I'm going to choose, we're going to start with the left side on this one. So we want to write down sine x cotangent x equals. And then we want to start thinking about, are there some things that we might be able to do to that? Any good ideas? What might we try, given the things that we have? So Jimmy. Okay, let's give that a try. Let's keep that sine x as sine x, and let's change cotangent to cosine x over sine x. What do you think? Is that going to help? Why, Kay? Okay, so we've gotten rid of that, and we just have cosine. Where are we trying to go? I've got cosine. I've got to somehow get secant in there. How do I do that? Oh, that's right. They're reciprocals. So since cosine and secant are reciprocals, one of them equals 1 over the other one. So I can just change cosine to 1 over secant, and that's my right-hand side. So once again, I have something equals the other side. That makes sense. And I do want to mention to you, when I'm doing these, a lot of times I'll say, oh, 1 over secant, but you can't ever write 1 over secant. You can't ever write that you're multiplying on the last one by sine over sine. You've got to have the argument in there. And if you notice, even though I said 1 over secant, or cosine over sine, I wrote cosine x over sine x, and so on. You've got to always have the arguments in there. So any questions on those before we move on to something a bit different here? Okay, a little bit of definition here. Even and odd, we know what those words mean when we talk about numbers. They're going to mean something different now that we're talking about graphs. When we're talking about graphs, Even means symmetric about the y-axis, and then we'll do odd in a moment on the next slide. So here is a function. It's not a trig function, but doesn't it look like the y-axis is a line of symmetry? Don't the left and right halves look like mirror images of each other? So since this is symmetric about the y-axis, this is an even function. Notice that means if I take opposite x's, like the 4 and -4 right here, they have the same y. Or if I take 12 and -12, they have the same y. So that's what this rule is saying. Opposite x's, that's the x and the minus x. But when I take f of those, then I'm talking about the y. And those are both positive or both negative. They aren't opposites of each other. So opposite x's have the same y. Think about your trig functions that you know. No shifts, basic sine and cosine. Is either one of those symmetric about the y-axis? So cosine is also symmetric about the y-axis. So cosine is even. And let's get the graphs up here so that we can see that. Maybe I can straighten this just a little bit. It's not too bad, but that's a little bit better. And then if I flip one of these, left and right, so the numbers get messed up when I flip like that, but don't the graphs still look like exactly the same shape? That's what it means to be symmetric about the y-axis. That one down and the one with the numbers looking normal, closer to where I can see what I'm talking about. So for this one, if I take 45 and -45 degrees, they have the same cosine, √2/2. So that means that for cosine, the cosine of one angle is the same as the cosine of the opposite of that angle. So what we'll see in a little bit is if we're doing a proof and we have something like this and we're trying to clean it up to simplify to get to the other side, it's okay with cosine to just change the angle from positive to negative. But that's not going to work for sine, is it? Sine's not symmetric about the y-axis. Odd functions mean they are symmetric about the origin. We can spin them 180 degrees and they look exactly the same. So let's take a look at our sine function. What do you think? If I spin that 180 degrees, will the shape look exactly the same? Well, let's try it out here. If I spin that one 180 degrees, even though the numbers are messed up, the shape looks exactly the same, right? When things are odd functions, if I take opposite x's, they have opposite y's. One is positive and one is negative. So if I take opposite x's, the x and the minus x, one of the y's is positive and one is negative. So if it is odd, opposite x's have opposite y's. So that means for sine that if we have the sine of minus an angle, and we don't want to have that minus angle for the argument, we can put a minus in front of it and say sine of theta. Okay, we've not yet learned to graph the tangent function. You're not expected to know it yet, but I'm just going to show you what it looks like so we can try to figure out if it might be even or odd. So here's your graph of the tangent function. And tangent of 0, 0, right? We've learned that. Tangent of 45 degrees, where I've got this purple dot. Tangent of 45 is 1. And I could tangent of 135 degrees is -1, and so on. And isn't tangent undefined for 90 and -90 degrees? So I don't actually have any points that are 90 comma something or negative 90 comma something or 270 comma something. I've got these vertical asymptotes in there. So what do you think about that one? Is it symmetric about the y-axis? No, it doesn't look like mirror images. Could I spin it 180 degrees and it looks the same? And thinking maybe, well, we'll take a look here. Does it look like the same shape, just the labeling's messed up? So that means this one has to be odd. So tangent is odd, which means if I take opposite angles, so theta and minus theta, I have opposite y's, so I have to have a minus sign in front of one of those. So let's get some of this written down where we can keep this part straight. If they are even, they're symmetric about the y-axis. Opposite x's have the same y's. If they are odd, they're symmetric about the origin, and opposite x's have opposite y's. And the best thing I've come up with for remembering this is odd and origin both start with O, so they're the ones that go together. It's more important to remember how the plus and minuses work than to remember what odd and even means. And so we have talked right now about whether sine, cosine, and tangent are odd or even. But now we're going to talk about all of the other trig functions. Cosecant, secant, cotangent, and what's going to be going on with those. Looks like we just about have that written down so that we can go on to the next page. So far we have said sine and tangent are odd. So the sine or tangent of opposite angles are opposite values. They need to have the minus sign added in. Cosine is even, so the cosine of opposite angles are the same as each other, not the opposites of each other. And then we want to fill in the other three trig values. And we're going to just think about these algebraically. You don't need to write down all of this extra, and I'll erase it in a moment, but for cosecant, cosecant is 1 over, what? 1 over sine, so 1 over the sine of that same angle. But I know that if I take the sine of a minus theta, I need to have a minus out in front. So I'm going to just have 1 minus 1 over the sine, but 1 over the sine takes me right back to the cosecant. So if I have cosecants of opposite angles, I do have to have the minus sign in there to say that they have opposite y's, which means that that is an odd function. For secant, I'm going to be doing 1 over the cosine. Do I need to put an extra minus sign in when I do 1 over the cosine? So that's going to just be equal to the secant of theta, which means that one is even. And finally, let's see, cotangent. I could do that cosine over sine, but that's going to be a lot of plus and minus signs to worry about. How else can I do cotangent? 1 over tangent. So if it's 1 over the tangent of minus theta, do I need to add an extra minus sign in when I work with tangent? So cotangent of minus theta is going to be minus the cotangent of theta, so that one is also odd. The only ones that are even are cosine and its reciprocal. And we're not done with formulas yet, so don't put them away. Questions up to this point? Okay, the last group of things that we're going to talk about today will be Why do we call them cosine and cosecant and cotangent? What do those names mean anyway? The way that we're going to answer that question, we're going to think about SOHCAHTOA, our basic right triangle trig that we've been using for a couple of years now. And when we do that, we have one 90-degree angle, and the other two angles, if one is theta, the other one's 90 minus theta, right? So those are complementary angles. So we're going to be thinking about the two complementary angles, which is going to be part of where the co comes in. So if I talk about theta, I can say the other angle is 90 minus theta. When I'm talking about a right triangle and I'm talking about the acute angles, the ones that we take sine, cosine, and tangent for. So we've got letters A, B, and C up there on that triangle. So think about SOHCAHTOA, and I need everybody to shout out. If I'm talking about angle theta, what is its sine? B over C. If I'm still talking about theta, what is its cosine? A over C. And what is its tangent? Okay, now let's go to the other angle. I'm going to go to the 90 minus theta. For 90 minus theta, for this other angle, what is its cosine? Sine of one angle was cosine of the complementary angle. And let's see, as long as I'm at 90 minus theta, what is its sine? Once again, sine of one angle is the same as the cosine of the complementary angle. So sine and cosine are co-functions, and when we talk about the angle and its complement, we get the same answer. So you see what's going on there? Okay, now tangent, you said for theta, was B over A. Cotangent isn't in SOHCAHTOA, so I'm going to wait a minute to talk about that one. If I am at 90 minus theta, what is its tangent? Is everybody good with that? All right, now we don't have SOHCAHTOA really for cotangent, secant, and cosecant, do we? So here's what's going on. Let's talk about tangent first. If tangent is opposite over adjacent, if we take the reciprocal of that, so we turn tangent upside down, we have cotangent. We have to turn adjacent over, or opposite over adjacent upside down, and we have adjacent over opposite. So because tangent and cotangent are reciprocals, they're upside down from each other, so the O and A's have to be upside down and also be reciprocals of each other. So now let's use that. If we are at 90 minus theta, and its cotangent is adjacent over opposite, what would that be for our letters? And if we are at theta, what would that cotangent adjacent over opposite be? So for tangent and cotangent, co-functions, if we take them of complementary angles, we get the same value. Think it's going to work for secant and cosecant? Probably, yeah, you're right. So secant is 1 over cosine, right? And cosine is opposite over, secant is 1 over cosine. Cosine is adjacent over hypotenuse, so this needs to be hypotenuse over adjacent. So for theta, what will its secant be? What will hypotenuse over adjacent be? C over A. I guess I shouldn't use A in two different ways. For 90 minus theta, what is hypotenuse over adjacent? C over B. Okay, cosecant is 1 over sine, right? Sine is opposite over hypotenuse. So this needs to be hypotenuse over opposite for our cosecants. So for 90 minus theta, what is hypotenuse over opposite? And you were right, those two matched up. And for theta, what is hypotenuse over opposite? So what we have from this is that sine and cosine of complementary angles are equal to each other. So if I have cosine of 90 minus theta in a proof, I can change it to its cofunction sine as long as I change the angle to its complement. And the same thing all the way down the list. So cosine means the sine of the other angle, the sine of the complementary angle. Cotangent means the tangent of the complementary angle. Cosecant means the secant of the complementary angle. And that will finish up our formulas. And I have one more proof that I want us to do together. So let me just give you a moment to get that all copied down. So again, when you're doing proofs, if you have these 90 minus theta things in there, you change two things. You change the function to its cofunction, sine and cosine, tangent and cotangent, secant and cosecant, and you change the angles to the complements. If it was 90 minus theta, you change it to just theta. Looks like we are just about there, just about ready for our last trig proof. Unfortunately, it's a short one, so you can be happy about that. So let's go ahead and run through that. So, got to decide which side's messier. How many votes for the left? Any votes for the right? Okay, we're going to start with the left. So we copy the whole left side down exactly like it is. Cosine minus theta times the sine of 90 minus theta. Now we have to use our even and odd stuff and our co-trig function stuff in this proof. So let's see, cosine. That graph said opposite x's had the same y's. So that means we change, if we change minus theta to theta, do I need a minus sign? No, that was the even one. It does not need the minus sign. And then I have one of these complementary angles, so I have to change two things. What's the co for sine? Cosine. So I'm going to change that one to cosine, and I need to change 90 minus theta to its complement, so it's just theta. Is that getting me any far closer to what I need for the right-hand side? Yep. But it doesn't look exactly like the right-hand side yet. Cosine times cosine is cosine times cosine, which we write this way. Now left equals right, and we have finished with it. Anybody with questions on what we have talked about today?